the 4th be with you. That's right. It's Star Wars Day, May 4th, 2020. Hope you had a great weekend. Hey, speaking of cool things in space, last night I'm out in my yard about 9 o'clock. And I look up and I see a satellite going across the sky. That's always kind of cool. You might ask, well, how do you know it's a satellite? Well, it's moving. So, process elimination. It's a satellite, it's an airplane, or it's a bird or bat or something. Okay? All right. I can tell it's not a bird or bat. Airplanes blink. Okay? Satellites don't. If it's a solid light, probably a satellite. 2, they move a little bit different. Satellites are faster as they go across the sky than your airplanes typically. I mean, it kind of depends on how close it is, but when an airplane is close enough to you that you see it moving that fast, you'll also definitely see the blinking lights on the airplane. So, anyway, I see a satellite. And I'm watching the satellite go across the sky, and I realize there's another satellite coming right after it. They're probably about, 10, 15 degrees apart. If you hold your hand out, a fist width at arm's length is about a 10-degree difference in view. So they were probably a good 10, maybe 15 degrees apart, maybe even a little bit more than that. I didn't measure. But there's a second satellite coming right after the first one. That's kind of cool. And then as I'm watching, there's a third satellite. And as I watch, I counted 9 different satellites, all following each other. And so I had an idea what that was about. Elon Musk's company, SpaceX, is launching a satellite network, which it's intended to be thousands of satellites. And it's going to be a broadband internet service. And their goal is to have enough satellites covering where basically every place on Earth, anywhere you go on Earth, you're going to have a good, strong broadband signal. It's a pretty ambitious idea. But these satellites are tiny. It's basically like, I think, kind of a squarish plate. I don't know how thick. But they launch these as a brick of satellites, like dozens, maybe even more. I don't know how many are in a brick. But this brick of satellites gets launched into orbit. And then the individual satellites separate from each other over time until each one has their own individual orbit. And so after they're launched, they're basically just this string of satellites in line with each other. It's really pretty cool. So I went and did a little bit of looking on my computer after I came inside and figured out that must have been from the Starlink 3 launch, is the satellites that I was seeing. Their time and position matched. And all these things you can find on the internet. Pretty cool. Now, I'm going to do the flip side of that. If you're an astronomer and you're going out trying to look at the sky, it can be annoying when you got all these man-made things that are going through. And when you think about this being thousands of these little satellites that are being added to what's already up there, I can see where people could get upset at that. Now, for me, this is the first time I saw that. It was kind of neat. That's kind of cool. But I could see where that could get old, too. It's like, looking out at a pristine landscape and seeing people's trash left behind. That gets a little bit annoying. Don't be doing that stuff, okay? I know I got one particular stretch of road that I drive on the way into town that's just littered in cans and whatnot. Don't do that. That's very, I don't know, very arrogant, very lazy, disrespectful. There's a lot of words for that. Don't do that. Anyway, those of you who are out in the country and have poor internet, sometime soon you might be able to sign up for broadband from Starlink. I don't know if they're already providing service, but I know they're planning on northern United States and Canada is supposed to be covered by the end of 2020. So it's coming soon. All right, so let's see some physics for today. We are starting a new chapter, and our chapter is going to be on momentum and collisions. Okay, so our learning targets for today are that you can define the word momentum and that you can perform some momentum calculations. And you can define the term impulse, and you can perform some impulse calculations. So, momentum in physics is the product of mass and velocity. Simple. Momentum is mass times velocity. Equations, a little bit weird. We use a lowercase p for momentum. I have no idea what the history of that is. I don't know why p is for momentum. But that's the way you see it. Uppercase P is power, lowercase p is momentum. So P equals m times v. Obviously, you can do algebra. You see m is p over v, v equals p over m. Labels. Mass is measured in kilograms, velocity in meters per second, and so momentum is in kilograms times meters per second. That's the label. There is no derived label that goes, like when we talked about energy was measured in joules. Well, joule was a Newton times a meter, and all those things. This is it. There's no specific momentum label other than this. Now, if we had a object that was small and not moving very fast, we might instead use grams times centimeters per second, or something like that. Okay, I do want you to be careful to realize this is not a Newton. A Newton is a kilogram times a meter per second squared. This is not this, okay? There's no squared on the seconds down here. This is a mass times an acceleration. This is a mass times a velocity. Momentum is not measured in newtons. I suppose you could call it Newton seconds. That would work. All right, let's look at page 191 from your textbook, problem number 1. By the way, when they were doing locker clean out last week, I walked by and there's a physics book laying on a table. So that kind of suggests to me that at least one of you out there doesn't have physics books at home. How in the world are you doing these assignments? If you need a physics book, you better let me know. That's not very reasonable, guys. Not very reasonable at all. Okay, problem 191. So we got a deer. So here's my little Rudolph. And the deer is running straight at us at 17 meters per second while we are driving north. So if we're driving north and the deer is running at us, I think the deer is running south. Okay? And we're just supposed to find, it's a big deer, by the way, 146 kilograms. It's a big deer. We're supposed to find the deer's momentum. So how do we do it? Well, equation. Momentum equals mass times velocity. I look at, I know the mass of the deer is 146 kilograms. I know the velocity of the deer is 17 meters per second to the south. Direction does matter. This is a vector quantity. Direction does matter for momentum, most certainly. So we multiply these two together. Got to grab my calculator. 146 times 17 equals, we only get 2 sig figs, so I guess this would be 2,500 kilograms times meters per second. No labels cross off. Got to keep them all. Simple as that, okay? Problems don't get any easier than that. Hey, before I forget again, I had some comments from a couple of students saying that sometimes there's kind of a bad glare on here, and I tried to look at them. I thought it was manageable, but I did change the angle of my camera here a little bit, hoping that there'd be less glare. I'd appreciate feedback letting me know if it's better or worse than what it was. All right, let's try another one. Mr. Rupp, 307 pounds, I'm going the wrong way right now, is jogging to the north at 3.0 meters per second. I realize some of you can probably walk that fast, but for me that's a jog, okay? How fast would Caden, 142 pounds, Caden, I really don't know exactly how much you weigh, but I took a guess, have to run to match Mr. Up's momentum? Okay, so I guess we have to know Mr. Up's momentum, mass times velocity. Now, mass should be in kilograms, but I want you to think through this. What happens if I don't change my labels here? Because what I'm going to do is I'm going to take mass times velocity here. Now my weight is proportional to my mass, so long as I'm on this planet. And if I just put in this, I get some weird labels. But then when I do this next part to find Caden, how fast would he have to run? I'd take velocity equals momentum divided by mass. And so if I figured out my momentum from this one and put it in here, and let's say I still had pounds in there, and then I took and divided by Hayden's, instead of mass, I use his weight in pounds, it's all going to cross off again. This is just a little tip to you that, you know, there are times where I wouldn't necessarily have to convert this label, because in the course of the problem, it's just going to cross out again. So I want to try that with you and see how that fits in your brain. All right, mass, 307 pounds is not a mass, but I'm going to plug it in anyway. Because what would I do? I would take 307 pounds divided by 2.2046 pounds per kilogram, right? But this is proportional. I'm going to go 307 pounds times 3.0 meters per second. .307 times 3 is 921 pounds meters per second. Okay, now it should only have 2 sig figs, but I'll round off at the end. Okay, so now I look at Caden running, and let's say he's trying to match my momentum of 921 pound meters per second, and we're going to divide that by his mass, only instead of mass we're going to use pounds there too. So then the pounds are going to cross right back off. So it's like I could have used that conversion factor of 2.2046 pounds per kilogram, and I'd have to divide into one step and then multiply in the other step, and it just cancels out. So if I understand that, I can skip through that. Okay, 921 divided by 142 is 6 point, again, now the final answer, we're only allowed 2 sig figs, so I'm going to go 6.5 meters per second. Does that make sense? I hope so. It's just a product of mass and velocity. I weigh a little more than twice what Caden weighs, and so therefore he would have to run a little more than twice as fast as me. Okay. Now, if that label stuff didn't make sense, then you just go and you convert that to kilograms, calculate your momentum, convert Caden to kilograms, calculate this velocity. But you see that if we leave pounds in this case, they're just going to cross off, and I'm still going to be left in meters per second. All right, what's next? Impulse. Impulse is the change in momentum. Okay? What's really weird here, you know, there's a couple weird things in this chapter. One is, why do we use P for momentum? Two, here we have this quantity, and these quantities before, we've always had a new symbol for it. Okay? But in this case, impulse is just talked as the change in momentum. So when we say impulse, we're going to say, well, delta P, the change in momentum. And impulse is equal to the force that you apply to an object times the time interval over which it's applied. Impulse is force times time. Now, change of momentum, well, how do you figure out that? Well, you take the mass times the velocity at the end, and you subtract the mass times the velocity at the beginning. Now, typically our mass of the situation doesn't change, so really what's just happening is we have the velocity changing. So I could take mass out of both of those and say my change in momentum is really mass times change in velocity. So I rewrote this equation over here. Impulse is m delta v, mass times change in velocity, equals force times change in time. Now, again, the mass has to stay constant for that to be true. But then this here becomes a very useful equation. So anytime we have a collision or something going on where something changes velocity, there's forces applied, we can figure out the things that are missing. All right, page 193 in your textbook, problem number 1. We got a football. The football is half a kilogram, 0.50 kilograms, and it's traveling, I believe, to the west at 15 meters per second. So therefore, you know, we got somebody over here that's catching the football. So the football comes over, this guy catches it and stops the football in 0.020 seconds. Pretty quick, you know, boom, stops the football. So what we want to know is, you know, so now the football is going 0. We're asked how much force was used to stop the ball. Okay? So we use impulse. And we say m delta v, which is my change in momentum, equals f delta t. I'm looking for force. So force equals m delta v over delta t. Right? Divide both sides by delta t. So what's the mass of my football? 0.50 kilograms. What's my change of velocity? The final velocity is 0. The initial velocity was 15. 0 minus 15 is negative 15 meters per second. Change in a quantity is final minus initial. 0 minus 15. Get that? Negative. Change was negative. And we're dividing by the time interval, which was 0.020 seconds. Let's take a look at labels. We have kilograms times meters per second squared. That sounds like newtons. And we're looking for force. Force is measured in newtons. Sounds like good news to me. 0.50 times negative 15 divided by 0.020. I've got negative 375 newtons. I'm only allowed 2 sig figs, so negative 380 newtons. What does the negative sign mean? It means it's in the opposite direction. So in this case, my force is to the east. Got that? Obviously, if I'm going to stop that ball, the ball's traveling this way, I got to apply a force the other way, the opposite direction. All right. Not sure if you can read this real well, so let me read through it. A 1,550 kilogram car loses control, goes off the road, and hits a tree. Bad news. The car is traveling 25.0 meters per second to the west when it hits the tree. So, tree, car, boom, okay? 25.0 meters per second. The car comes to a stop, so final velocity is 0 meters per second. The time it takes to stop is 0.100 seconds. What force does the tree? Oh, mass of the car, 1,550 kilograms. So what force? All right. So we do a impulse problem. M delta V equals F delta T. We're looking for force, so force equals M delta V over delta T. Mass of the car, 1,550 kilograms. Delta V. It started out 25 meters per second. It finished at 0 meters per second. 0 minus 25 is negative 25.0 meters per second. The change took place in 0.100 seconds. We're going to get kilograms times meters per second squared is newtons. 1,550 times negative 25 divided by 0.1. Wow. Negative 300, and I'm going to go with 3 sig figs here, 388,000 newtons. Now, a newton is a pretty small unit of force, but that's a lot of newtons. Car crashes are serious business. So, that's the force. What direction? Well, the negative sign says it's the opposite direction. So in this case, it'd be east. Okay? And now, there was another question here. It says, what would be the force if it took 0.200 seconds to stop the car? Well, notice everything would be the same, except this time down here would be twice as big. Now, if you make the denominator bigger, you make the overall answer smaller. In this case, if we double the denominator, we're going to cut this in half. So I'm going to divide this by 2. And now we've got negative 194,000 newtons. That still sounds a lot, but I mean, look at that change in force. So this is why on cars, we design cars with crumple zones. So when the front end of your car hits that tree, and I hope this never happens to you, I sincerely hope that. But when that front end of that car hits that tree, it doesn't just stop there. What happens is the front end starts to crumple up and the car continues to move a little bit, and it lengthens the time it takes to stop the car. And lengthening it from 0.1 to 0.2 seconds is still, 0.2 seconds is still really fast. But it's twice as long. It cuts the force in half on the occupants of the car. And in some cases, it allows the occupants to survive crashes that on cars of years gone by, you wouldn't have survived. So those energy absorbing features of cars are tremendous. That doesn't mean you want to try to test their limits, but they are amazing pieces of technology that are in our cars. All right, so there's an introduction to momentum and impulse. I assigned you some problems to practice. We worked out 2 of them here, so that leaves you a few other ones to do. Good luck. May the 4th be with you.